Solar panels may look like simple blue tiles on rooftops, but the process that transforms sunlight into electricity is a carefully engineered chain of scientific steps happening at both microscopic and system-wide levels. Each solar panel is built from many photovoltaic cells made primarily from crystalline silicon, a semiconductor chosen because it releases electrons easily when exposed to light. These cells are engineered using a method called doping, where one side of the silicon is treated with phosphorus to create extra electrons, and the other side is treated with boron to create positive holes. When these two layers are joined, an internal electric field forms at the junction, acting like a one-way gate for electrons. Once sunlight strikes the surface of the panel, its photons, tiny packets of solar energy, penetrate the silicon lattice. If a photon carries enough energy, it knocks an electron loose from its atom. Instead of wandering aimlessly, the built-in electric field pushes the freed electron in a single direction, creating the flow of direct current, or DC electricity. Since a single photovoltaic cell generates only about 0.5 volts, manufacturers connect dozens of cells together in series and parallel combinations to build a solar module that produces usable voltage. Multiple modules are then combined into strings and arrays that can power homes, schools, industries, and massive utility-scale solar farms. But this is only half the story. Homes and factories use alternating current, or AC electricity, which means the DC power from the solar array must pass through an inverter. Modern inverters not only convert DC to AC, but also track the panel's maximum power point, compensate for shading or cloud movement, protect the system from voltage spikes, and synchronize the output with the grid's frequency. Once converted, the electricity flows through the home's distribution board to power appliances, machinery, or lighting. If the system produces more energy than the household consumes, the excess can be stored in lithium or LFP batteries for nighttime use, or sent back to the utility grid through net metering, which can reduce or offset monthly energy bills. Although solar panels convert only about 20 to 23% of sunlight into electricity, many factors influence their performance, such as the angle of installation, geographic location, temperature, dust buildup, panel orientation, and shading from nearby buildings or trees. Dust alone can reduce efficiency by more than 10% if maintenance is neglected. Heat also plays a surprising role. Silicon panels lose efficiency as temperatures rise, which is why airflow behind the panels is important. Despite these limitations, solar technology has evolved quickly. Innovations like half-cut cells, PERC technology, microinverters, bifacial modules that absorb sunlight from both sides, and experimental perovskite coatings are pushing efficiency higher while reducing cost and installation complexity. Solar farms now integrate tracking systems that rotate panels to follow the sun, capturing more energy throughout the day, while smart home inverters can optimize power use between the grid, batteries, and critical loads. The result is a mature, highly reliable energy solution that converts a free and abundant natural resource, sunlight, into a powerful electrical supply with almost zero ongoing cost. And when you consider that the amount of sunlight hitting Earth in just 1 hour could power the entire world for a full year, it becomes clear why solar energy has become one of the world's fastest-growing and most promising clean energy technologies.